Okay, so now we're going to talk about alternating series. Now, what an alternating series is, excuse me, is basically something where you have like the first term is positive, the second term is negative, like you see here, and then after that you have like the third term is positive. So it keeps alternating between positive and then positive and negative as you go on with the sum. Okay, so each term basically goes from positive to negative. Now, what that does for you, okay, we're gonna basically focus on this one right here. You have this series on the right. What happens is when um when you plug in the first number, which is one, all right, you're gonna get a positive number or zero. Now we're gonna focus on that because that kind of leads us into our alternating series test. Now I kind of wrote some stuff on here to hopefully understand when you have an alternating series, the sums kind of oscillate back and forth as you see here, right? S of one is one, S of two is one half, so it kind of keeps going back and forth. Now to figure out if the alternating series test, right, is going to be used when you have the three following conditions, and if those three conditions are met, then the series will converge. All right, so first of all, every a of n has to be positive. Now, a of n happens to be this part. It's just the part that's actually the sequence, not the series. Okay, so now normally I have this, I kind of do that one before then. It has to be decreasing. Okay, so this is what that means. This is just a really fancy way of saying decreasing. And then also it has to the limit as n goes to infinity of the sequence has to be equal to zero. If those conditions are met, then the alternating series is actually gonna converge. Okay, now verbally speaking, a series converges if its terms alternate in sign. So every term, like what I had up there, right? I had a positive one, then a negative one half, then I think I had like a what I have here, a one third, and so on. Let's see what the next term was. One negative one fourth, and so on. So as you can see, the signs keep alternating, all right? But every term on the sequence has to be positive. So for example, if I just write the terms down, all right, without worrying about the sign, this actually would be the sum, and this would be like the terms, all right, the terms of the sequence. So I just want to make sure we understand that. Now, if you don't understand, that's fine. We're gonna do a few examples, and hopefully it'll become clear. Now, it has to be decreasing in magnitude and has to have a limit of zero. So we're all good there. So now let's take a look. Now they have a word of caution here that basically says that the alternating series test can only prove convergence. All right. Basically, it says that it cannot prove divergence. All right. So if it doesn't fit, if you're doing the alternating series test and one of those conditions failed, it doesn't necessarily mean that we'll diverge. Okay, now we can use the nth term because it's almost the same thing, especially this is almost like the last condition to figure out if something diverges. But again, I might go to the homework and show you one that what they say here applies, because I don't think they have one on here that actually applies. All right, so first we got to do the following. All right, first of all, is this an alternating series? It is, right? You can kind of look at it. If I plug in a 1 for n, I get a negative. If I plug in a 2, I get a positive, and so on. If I plug in a 3, I get a negative. So the first thing I have to figure out is a of n. Now, this right here, I could rewrite it like this, and that's the key part that is really simple, but it's not. You could definitely miss it if you don't do it like this, okay? I could really separate this like this, couldn't I? Couldn't I not? I could, right? Now, this part right here is what I'm talking about that has to be positive, okay? So only that part is the part that I care about here. So is this going to be positive all the time? The answer is yes, okay? Now, the second condition that I kind of flipped on you is basically I have to figure out if this is decreasing, right? The first term, for example, if I had like the first term, I would have a 1 or a 1, then I would have a, let's see, 1/4, and that would have a 1 over 9, and so on and so on. So as you can see, this is decreasing. And something that do say on there, and I guess I might as well highlight it, is that they actually say on this one, I don't know why I didn't write it at the beginning, but they actually said that it has to be decreasing or it has to be equal to. So you may see it like this, and it just means the same thing. But so it can be equal to also, because I think you have a couple in your homework that as you do them, the first two terms are the same, but then after that it starts decreasing. Okay, so this means the same thing. All right, so now number 3, we have to make sure that the limit as n goes to infinity of the sequence, which is this, has to go to 0. Now it does. In this case, the limit does go to 0, so therefore it converges by the alternating series test. I think my wife is watching American Idol. I hope you can't hear that. As a matter of fact, I'm going to pause this second, tell her to turn it down. So hang on just a second. Okay, continuing on. All right, so let's go to example B. Same idea. Now I have to figure out what A of n is. Kind of easier to tell what that is because it's just right here. They can already separate that for you. Okay, so I have to go through the same steps. I'm going to write every one of these down. So is this part right here decreasing? Well, I meant to say, is it greater than 0? Is this going to ever be negative? And it's not. Okay, so now the second part is I have to figure out if it's decreasing. Now, if you can't tell if it's decreasing, just plug in a few points to see if it is, all right? And in this case, it is decreasing. Okay, now number 3, I have to figure out what is the limit as n goes to infinity of n squared over n cubed plus 1. Now, using the horizontal asymptote rules, this will be 0 also. So therefore, it will converge by the alternating series test. Okay. All right, so let's go on to the next one now. This one's a little bit more difficult, but this part right here also is that's just my series. Excuse me, my sequence. So I have to figure out if that sequence right there is going to be greater than 0 or positive all the time. It is. Right, on number 2, I have to figure out if that's decreasing. And again, you can plug in a few points. I think I did. Let me actually write them down. I kind of notice, for example, this one right here, you have the same term here. Right, both of those are 1/2. But then after that, it starts going down. So 1/4, and then 5/32. So you can do as many as it takes for you to convince yourself. So it is decreasing. I'll write it the other fancy way that I have here. So I'm just saying that the next one over is at least less than or equal to the previous one. That's what that means. All right. So it's decreasing for sure. Now, on example the third thing that I have to have for this to be convergent is I have to take the limit as n goes to infinity of n over 2 to the n. And then now for some of my problems on the homework, this is actually the kind of the hard part to figure out if this was convergent, by taking the limit. That was a hard part for me. All right, now on this one right here, there's really a couple of ways to think about it. They're both definitely infinity if you put them in there, but you have to figure out which infinity is bigger. Now, at the bottom infinity is bigger because you have an irrational function. So as this denominator, as it gets bigger and bigger, right, it's going to get bigger faster than the numerator. But in case you don't see that, You could, if you want to, since they're both infinity over infinity, right? You could do L'Hopital's rule. Which means I have to take the derivative of the top, which is just 1. The derivative of the bottom, that's an exponential function, which we normally don't take a whole lot of derivatives of those, but here's the formula. I have the natural log of 2, which is the base of the exponential, times the power, which is n. All right, so as I plug in infinity into this, you'll see that this is 0. So therefore, this will converge. Okay. So D is an interesting case because this will not be decreasing the entire time. All right, so I'll just go through the process just to let you know what you could do in case you couldn't figure out. So the first thing is, this going to be greater than 0? I think hopefully you can tell that if you, and I'll write those down in a second, if you were to just write all of these, just the sequence, not the series, right? So I don't care about the sign right now. You could tell that all of these, hopefully, you can tell that all of these would be positive. Right, so it will meet the first condition. Now, the second part is a decreasing. Okay, now, if you didn't have a calculator to look at the graph of just this part, what you could do is you can use a derivative to prove, or I could say take the derivative to prove that it's decreasing. Okay. Now, why would that matter? Well, remember, if the derivative is negative, right, then that means it's absolutely decreasing. So I'm going to call this function f of n. So f prime of n, I would have to use, what do I call it? Quotient rule. So I have low d high, the derivative of the top is 1 over n, right? The derivative of natural log of n, minus low d high minus high, d low, which is just 1, all over low squared. Okay, now, what is this equal to now? Okay, so to figure out the rest, what I would have to deal with here is I would have to set this equal to 0 to figure out the rest. Now, in this case, I only care about the numerator. Now, notice that this right here is going to be, it's going to be 1. Okay, so I have 1 minus the natural log of n is equal to 0, and I would have to solve for that. Now, if I have that, I take the e, or I exponentiate each side. So that would leave me with n is equal to e. Then I have to do the sign analysis of this. Now, n cannot be equal to 0. Okay, then I have to basically plug in something bigger than e, or something less than e, like 1. 1 would be a great example. If I plug in a 1 back into this right here, natural log of 1 is 0, so I'd have 1 minus 0 over 1. So that will be positive, which means it's increasing on this side. And then after that, if I would plug in some really big number, it doesn't matter, some ridiculous number perhaps, notice that this will become really negative, all right, over a positive, because n squared doesn't matter what you plug in for n on the bottom, you're still going to get positive. So you have a negative over a positive, so this is going to be a negative. So negative divided by positive is negative, so this is going to be decreasing. All right, so it is decreasing, but it's only decreasing basically when the function is greater than e, okay? So at that point, Yes, this is true. Well, maybe I should explain what A of n is. A of n is this. Number 2, is it increasing or is it decreasing? Well, yeah, but I have to at least tell you that it is only decreasing when n is greater than e. Okay, so there is some kind of limit to that, or I shouldn't say limit, but a domain to that. And then finally, number 3, if I take the limit as n goes to infinity of natural log of n over n, is that going to be 0? Well, again, on this one, you could use L'Hopital's again. Okay, and if I use L'Hopital's, the derivative of the top is 1 over n. The derivative of the bottom is 1. So the limit as n goes to infinity of this would be 0. So let's check out. So therefore, this is convergent. Now we're going to talk about the alternating series error bound. So there's a way to approximate an alternating series, all right, which is not a super difficult problem, but mainly what it's going to teach you is going to teach you to find the error involved and the approximation that you found. Okay, so basically, this is like if you have your error. Let's see, partial sum useful to approximate. You can find your error by doing your partial sum, like your actual sum minus your partial sum, and that's going to give you the error. Now, if the convergent alternating series satisfies the condition of this, which means it's at least decreasing or equal to, okay, so if it's decreasing, so the stuff we've been doing mostly, rather than the absolute value of the remainder involving approximating the sum is less than or equal to the first unused term. All right, so blah, blah, blah. Let me just get to the first problem. Now, is this estimate? I hate the exploration crap. Okay, so on this one right here, notice that they went all the way to 9. I think this would be like, technically this would be like A9 here. This is the A9 term, okay? And it says can be approximate to an error of 0.01 by adding together. So the next unused term, right? So if I would keep going, that would be 1 over 10 squared, which would be 1 over 100. To be precise, negative 1 over 100. Right? It says, therefore, the error in your estimation, and I can find that, and I'm already showing you this, by taking the absolute value of the unused term, which is 0.01. Okay? Now, if we use our calculator, by the way, and I think it's math 0, if I'm not mistaken, to do the sum, or to find this option on there, on the 84. If I do that, then I get 8.822455. Now, it says, what's the error of the estimation? Well, to find the error, okay, we're going to take the absolute value of the next unused term, which is the 201st term. So if I would go back to this right here, all right, let's see if I plug in at 201, that's still going to remain, let's see, well, I guess it doesn't matter, it's the absolute value. Let me see, make sure here. See, negative 1 to the power of 202 divided by 202 squared. And that would give you your estimated error, which is the one that they're looking for here. 0.000025. That's what you get that. Okay. Now, let's take a look at the next one right here. I'm going to go through it relatively quick because I don't want to take too long on this part. All right. So now, they're asking us to write the first 4 terms, right? So I'll quickly write it. Or that's a 1 factorial That's approximately this, which is about 5/8. Now it says explain why the estimate found in A differs from the actual value by less than 1/100. Okay, so what I can do on here is I can go my error. Let's see, I can go to the next one. Okay, so I'm going to figure out my error is going to be the next unused term. Now, because I wrote 4 terms in the series, I'm going to go to the 5th one. All right, so I would have a -1, absolute value, excuse me, of -1 to the power of, let's see, 5 minus 1 over 5 factorial. That gives me 1 over 5 factorial, which is 1 over 20. 1 over 120, excuse me. All right, so 1 over 120, or it happens to be, if I put that in my calculator, 0.00833, which is less than this one right here, because this one is actually just 0.001. No, 0.01, excuse me. Yeah, 0.01. So therefore, this is why that's true. Okay, so there's not a whole lot of things to do there. Now, it says use your results to explain why the sum cannot be equal to 0.7. All right, well, the reason that it can't be, all right, is because this error that I just found previously. All right, so basically my answer should be to that, like the actual answer to the sum is going to be what I found here minus my margin of error for this one. This would be the lowest. And the highest, it would be this sum again plus my margin of error. Right? And if you put that on your calculator, this is what you would get. All right. So, moving on to the absolute and conditional convergence. So you do have something called absolute convergence, which means that if your series in particular is converging, and also the absolute value of the same or the sequence, excuse me, of the sum is also convergent, then this whole thing can be absolutely convergent, right? If it's absolutely convergent. Okay, so basically this is what I'm saying right here. And then a series is conditionally convergent if the sum of A of n is convergent, but the sum of the absolute value of A of n is not convergent. For example, right, on this one right here, okay, I will let me switch pages here. Okay, so here's the deal. If I take the absolute value of this inside of the sum, then what I would get, it doesn't really matter what I would have here. This would always be positive. So I can actually rewrite this as 1 over n. Now, this happens to be one of the P series series where P is 1. And if P is 1, then 1 over n, or this right here, is diverging. Okay, now here comes the weird part. Now, this is an alternating series that happens to be, well, I don't want to write too many symbols here. Where this is greater than 0. What was the next part? Is it decreasing? Yes. And the number 3 is the limit. as n goes to infinity of this equal to 0, and it is, right? So this is actually converging. But the absolute value of that same function is not, it's diverging. So this is why we're going to call this conditionally convergent. Okay, so let's go on to B. Okay, so now on this one right here, same idea. We have, if I take the absolute value of this, the long story of this one is that this is going to end up being the same as this, and P is equal to, it's a P series where P is equal to 2, and if P is equal to 2, since 2 is greater than 1, then this is convergent. All right, so again, the absolute value of that is convergent. Now, is this an alternating series that I can figure out if it's convergent or not? Well, it turns out that this is one of them. Yes, that's greater than 0, which means it's positive all the time. Yes. It's decreasing. Yes, it is decreasing. And the limit as n goes to infinity of 1 over n squared. Okay. So basically I'm still doing the alternating series test. This is basically the second part. So this is also 0. Now, because this is also says the alternating series is convergent, but the absolute value is not, since both of these are convergent, then we can call this absolutely convergent. All right. So let's go to C here. Now I could rewrite the absolute value of this, right? Not to bore you again. The absolute value is going to make that basically null, and then 0.01 could be written as 1 over 100. So all of this to the nth power. So this is a geometric series, and because the inside of this, what we call the r, is less than 1, or the absolute value of that is less than 1, then this is a converging geometric series. And then after that, I have to figure out if I can actually do the alternating series test on this. By first, is this always positive? And it is. Is this equation right here decreasing? It is decreasing. And number 3 is the limit as n goes to infinity. Let's see, is the limit as n goes to infinity of 1 over 100. Is that 0? And it is, right? So this is also convergent. So this is going to be absolutely convergent. All right, last but not least, on D, by the way, notice that this is an alternating sequence because when you plug in a 1, you get the cosine of pi, which is negative 1. And if you put a 2, you got the cosine of 2 pi, which is positive 1, and so on and so forth, right? So you're going to go between 1 and negative 1 on the top part. So this is going to be an alternating series. And I could rewrite that, right? Because that's really not going to matter. This just tells me positive or negative. If I take the absolute value of that, I can basically ignore the numerator and I can just say this is the same thing as this. Okay? Now, as you well know, because I literally feel like I just did that one, the P series, this part is convergent. And then now I have to do the same steps where number 1 is this, basically it's going to be the same problem as this. So I'm going to go ahead and tell you that it is absolutely convergent. No different. And then now let me see if I can pull a problem where you have something that is neither conditionally convergent or absolutely convergent. It's actually divergent. All right, just to avoid some confusion. Let's see if I can quickly pull it up here. Okay, let me look it up here. Let's see. Here, let me go get my homework because I need to look at it before I tell you this. Oh man, my back. Oh, here's my homework. Okay, so let me look. Because at first I wasn't very sure about what they meant by that, but then I figured it out. All right, so let's look at 15. All right, so on 15, this is definitely going to be an alternating series, okay? Now, here's the problem, okay? The alternating series and the nth term test are exactly the same in one particular thing, which is this. If I take the limit, so at first, I did all the same things you saw me do earlier. Yeah. Well, there's a couple of things that tell you that the limit, you can't really use the limit test. Is this greater than 0? Not all the time. So there's a lot of things that make this it makes it where you can't use the alternating series test, all right? So what I'm saying is that if you take the limit, so again, the alternating limit test, or excuse me, the alternating series test can only tell you if something is convergent, but it can't tell you if something is divergent. But if I take the limit as this goes to infinity, now if you just think about it briefly, all right, you don't have to like really, really think about this forever, but it doesn't matter what you plug in here. That's just going to be basically oscillating between 1 and -1 the entire time. So this, the limit does not exist. All right, so this is going to be divergent, not by the alternating series test, but is going to be by the nth term test. Which I think I wrote in your notes earlier, right? So let's look at number 13, for example. So number 13, I kind of did the same thing, and I was just kind of like, oh, this is obviously... Okay, so first I didn't know. I basically had to figure out a way to figure out if that was convergent. And the only way that I found is by doing the nth term test. Now on this one, okay, if I take the limit, and you can figure out that it is, that is greater than 0, that is decreasing, all that stuff could be true. But if this part right here is, if the limit as n goes to infinity of n plus 1 over 3n plus 1 is not 0, in this case is 1/3, all right, if that happens also, it has to be 0. And if it's not, then this is going to be divergent by the nth term test. Okay, let's see. So just be careful with that. Notice that this step right here is basically the third thing you have to have for something to be basically converging on an alternating series test. Yeah, same thing would happen on number 3, okay? But anyways, I'll just wait for you to ask me questions when you see me. So hopefully this helped and it wasn't horribly long. I apologize if it was.